Hi guys, welcome to this short tutorial video on IP QoS. So we'll briefly talk about the whole idea behind IP QoS, how deep subdomain is used to implement it, how IP traffics or packets are classified, shaped, dropped or forwarded to maintain quality of service over IP network. We are heading towards the converged IP networks on which all possible traffics like data, TV, video, voice, real-time gamings are transported. Triple play traffics are increasing exponentially day by day, and video on demand VoIP services are gaining their popularity among all classes of users. Now think one thing that you won't mind if a file or an email will take 3 more seconds to get downloaded in your system due to network congestion, but you will be annoyed enough if your friend's voice comes every time with a delay of 3 seconds to you when you are using a VoIP application like Hangout or Skype. And that is one of the key issues where quality of service is hampered. Although voice traffic is not bandwidth hungry like HD videos, but it is extremely delay sensitive. But IP traffic or IP networks were not initially meant for these kind of delay sensitive traffics, but for error sensitive traffics like email or data. One straightforward solution to handle the congestion of network which causes delay in packet arrival is to add bandwidths, right? Add bandwidths to the existing network. But it is not always possible because it incurs extra cost and it is not a permanent solution as well. Alternatively, a sustainable solution is to prioritize delay sensitive traffics over error sensitive traffics, or traffic from privileged customers, say gold customers who are paying much more amount for their bandwidths, over the traffic from low level customers who pay much less money for his bandwidth. And this is the whole idea behind IP QoS: prioritizing traffic, prioritizing IP packets. Now, to prioritize a packet for immediate forwarding, a router or switch needs to identify that packet first. Now, what type of packet that is? It should be classified without any delay, because we shouldn't effort quite a long time to classify the packet first and then decide whether it should be forwarded immediately, or we can keep that traffic or that packet waiting while other traffic could be forwarded. Internet Engineering Task Force or engineers were working for decades to classify more granularly the incoming IP packets, and you know that they're playing around the 8-bit long field of IP header. That the field is called type of service, which is marked here in the slide, and there are several. Actually, they have already proposed several solutions for that, and they're termed as request for comments or RFCs to address these issues. I have mentioned a few well-known RFCs here on the slides. If anybody feels to read more, can go to IETF websites for more details on their specific RFCs. They defined the differentiated service domain or deep serve domain by taking first 6 bits of the TOS domain. The last 2 bits domain, the last 2-bit domain is known as explicit congestion notification domain or ECN. When a router or switch experiencing congestion in the network, it can set this 2-bit as 11 for an IP packet. 01 or 10 notifies that the node is ECN capable. And if ECN is set to 00, that means that node doesn't have ECN capability at all. The code written in the deep serve domain, or the values of the deep serve domain, is called as DSCP. I will talk about how a router or switch marks this code in a moment. Earlier in RCF 791, known as IP precedence, which I have not mentioned here explicitly, that used only first 3 bits to classify traffics. Hence, we could get only 2 to the power 3, that is 8 different classes of traffic. But moreover, in that IP precedence, the probability of dropping different packets belong to a same class was not defined. So to classify packets with more granularity and with an added option of dropping probabilities of low, mid, and high, they have come up with RFC 2597, known as assured forwarding. Assured forwarding is most widely used in corporate environments today. As I told earlier, the table shows how different DHCP values classify the incoming IP packets. The best service will be experienced by the packet of low dropping probability packet of class 1, and the worst will be the high drop probability packet of class 4. Once this classification of packet is done, the similar packets are grouped together called behavior aggregates or BAs. The differentiated service approach to provide end-to-end QoS in networks thus defines small bit pattern in each packet in the IPv4 TOS octet, which is used to mark a packet to receive particular forwarding treatment or per hop behaviors, in short PHBs, at each network node. Every service provider defines service level agreements or SLAs with its customer. Customers may be classified as gold, silver, or bronze for their bandwidth they are paying for. As per the SLAs, each node is having a DHCP to PHB mapping table. Once packet is aggregated under a specific BA, the node can mark the DHCP domain from its DHCP to PHB mapping table. And as told earlier, the packet is going to get treatment from the further nodes as per the DHCP values. There are 4 globally recognized PHB groups, as it is shown here. If all the diffsub bits are set to 0, it is a traditional best effort packet and not a QoS packet. And this packet will not get privileged treatment throughout the network nodes. But this best effort packet, as I told earlier, as we are heading towards a converged IP network where traffic means real-time traffics are getting increased means day by day exponentially. Only best effort is not enough. That is why IP QoS. That is why we are talking about IP QoS now. Again, that expedited forwarding or EF is very useful for VoIP. It is another recognized PHB, and it is of low jitter and low delay. VoIP are generally forwarded through EF. We have already talked about the 12 PHBs of AF, that is assured forwarding. Class factors are there, which define 7 PHBs like IP precedence, IP precedence, and this slide is covering the all four globally recognized PHB groups. Well, there is an important concept of diffsub regions when different routers need to be configured with different DHCP policies, hence different DHCP to PHB mapping. But then how the different routers will know about the change of service agreements? A question here naturally crops up. So for this, traffic conditioning agreement or TCA is implemented. The edge routers peer to each other to exchange the information on what traffic shaping is required for both ingress and egress traffic. Well, incoming traffics are known as ingress traffic and outgoing traffics are known as egress traffics. Now we will discuss the different diffserv actions which are performed on ingress and egress traffics. For ingress packets, the actions are together called traffic conditioning and include classification, marking, and policing. First, an ingress packet is classified by checking what type of transport protocol it is used. The source and the destination port numbers, ECN, etc. may be investigated for multimode checking. Once the packet is classified, the next action called marking is done. It is all about setting the DHCP field by checking the DHCP to PHP mapping table as created by the BA agreements. Now, after marking, one more thing needs to be done or needs to be ensured that the rate of incoming traffic from a customer should not be greater than the bandwidth for which the customer is paying for. This action is called traffic policing. If a packet is found with rate within the agreed SLA, it should be allowed to forward. But if it is not, then two things could be done with it. One is drop the packet or forward the packet by remarking its DHCP with increased probability of dropping value. It is done by a technique called token bucket. Well, in a nutshell, token bucket is a technique used by the vendors to calculate nominal bit rate of arriving packets. One thing to mention here that the generalized formula for calculating bit rate, which is bit rate is equal to bits upon the time taken, is not applicable in packet environment. This trivial relation doesn't hold in packet environment because here packets are of variable sizes, involves inter-arrival delay, and moreover only a complete usable packets are taken under consideration. And for egress traffics, the actions are together called traffic shaping, includes queuing, scheduling, and congestion avoidance. First, queuing keeps the packet in a queue until the port is ready to forward the same. Once there are packets waiting in the queues, they need to be emptied, right? And this process is called scheduling. The combination of traffic queuing and scheduling is known as traffic shaping. Lastly, congestion avoidance is performed by dropping packets randomly to slow down the input to the queue when the queue is almost full. Hope this video helps you understand the basic idea of IP QoS and its requirements. Thanks for watching.